find the Maclaurin series for the function sine of x and its radius of convergence. Maclaurin series, I see the word Maclaurin series. That automatically tells you what you're centered at. What am I centered at? What? 0. That's my A value is 0. Anytime you see Maclaurin, automatically think A equals 0. So I always start these problems with my table. Once I know my A value, n, take the nth derivative, plug in A, which is 0 for me, this problem. And then the very last column is my coefficients, Cn, which is nth derivative, plug in 0 over n factorial. Okay. So let's do 0, 1, 2, and 3 like I've been doing. And I like to fill out a single column at a time because you're focused in on one task at a time. It's kind of a little bit easier than switching back and forth between these calculations. It makes it a little confusing. So let's start. My function was sine of x. What's the derivative of sine of x? Cosine. Okay, great. So now you want to take the derivative of cosine. Negative sine. And then the derivative of negative sine. Negative cosine. Okay. So we've completed that whole column now. So I'm done taking derivatives, so I'm going to move on to the next column, which says all I got to do is plug in 0 into each one of these in the previous column. So let's start by plugging in sine of 0. That's going to be 0 because it's your y value on the unit circle. Cosine 0, 1. Negative sine 0, cosine negative 1. Okay, so we're done with that third column. Let's move on to the fourth one. We just divide each one of these by n factorial. So I'm going to have 0 over 0 factorial, which is 0. I do simplify if the coefficient is 0. Okay. 1 over 1 factorial, I'm going to leave that alone. 0 over 2 factorial, that's 0. And then negative 1 over 3 factorial, and I'm going to leave that alone. So if you look, 2 of our coefficients are 0, right? My constant term and my coefficient in front of x squared. What is estimated tell me? It says you're taking the nth derivative. So here, I'm taking the 0 derivative, which means it's just the function. 1, it means I'm taking the first derivative. 2, second derivative. 3, third derivative. Same thing for the second column? For the second column, it says I'm taking the nth derivative and I'm plugging 0. So that's the difference here and here. Really, as you go across, each column kind of comes from the one before it and so forth. Yeah.
On 1, I'm not sure how you get the 1 on top. Like, how's it coming to be 1 over 8?
So I'm taking this one, that's the numerator, is the third column, and I'm dividing by n factorial, and n is in the first column. So you're taking these as your numerators, 0, 1, 0, negative 1, and then you're dividing by n factorial, so divide by 0 factorial, 1
What about
factorial.
the multiplication by the 0? That's what I'm not understanding.
What multiplication?
Oh, you're not plugging into CN? Or are you?
No, this is what Cn is equal to.
Oh, okay.
It's equal to this.
Oh, okay.
So if you notice, 2 of my coefficients out of 4 are 0. So that means I'm only getting 2 coefficients here. Really, 2 is not enough for us to get a pattern. You have to have a few terms. I usually say at least 3 to figure out a pattern. So I need to make this table a little bit longer. So I'm going to go back and make this table longer. I'm going to put in more rows into this table. So let's say I do, I don't know, let's do 4, 5, 6, and 7. So let's fill in our derivatives now. So you take the derivative of minus cosine. Cosine is minus sine, so it becomes a positive sine of x. But if you notice, that's the function we started with, right? So what's going to happen is now that we're now back at the beginning of our table, so I don't have to do any work to compute more derivatives. I just copy down what's in the table. Because I just keep taking derivatives, so it's going to follow the same pattern here. So you're going to get cosine x minus sine x minus cosine x. So that's nice when you have sine. If you take enough derivatives, you end back up at the same function you started with. So every 4 terms, this table is going to repeat itself. So if you notice, these 4 that I added in match up with these 4 that were up at the beginning. So these numbers here are going to be the same as the numbers that were up here. So you should be getting 0, 1, 0, negative 1. And our final step is we need to divide by n factorial. So for this one, I'm getting 0 over 4 factorial. This one, I don't organize these well, it's hard without lines. 0 is 1 over 5 factorial. And then 0 over 6 factorial. And then negative 1 over 7 factorial. So we have this big table, but let me kind of highlight for you which ones are not 0. This one, this one, this one, and this one. So every other term is 0 and every other term is not 0. Okay. So these are our coefficients. So let's go ahead and write down the pattern for our Maclaurin series. So Maclaurin series says I take, the formula is Cn x to the n. So let's write out some of the terms. My constant term was 0, and then I had, let's see, it was 1 over 1 factorial, x plus, it was a minus really, so maybe I'll make that a minus. Minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th, and then a minus 1 over 7 factorial x to the 7th plus dot dot dot. I think we finally have enough terms now. We can see what's going on. First thing that stands out to me is that these signs are flipping, right? Positive, negative, positive, negative. It's an alternating series. So let's see. I'm going to write out my summation symbol. Let's say I'm going to start at 0. So it's going to be either -1 to the n or -1 to the n minus 1, but the first term is positive, so it's going to be -1 to the n. So I've taken care of the fact that the signs are flipping. But now look at our powers. 1, 3, 5, 7. Those are all odd numbers. I'm getting no even numbers. So my powers are going to look like, I want it to be an odd number. So to get an odd number, we're going to have to write x 2n plus 1. And then 2n plus 1 factorial, because the factorial matches my exponent on x. And that is our Maclaurin series for sine of x. So we noticed it was alternating, right? Which tells me that anytime I have an alternating series, you're either going to write -1 to the n, or you'll write -1 to the n minus 1. Those are your two options. And it all depends upon if your first term is positive or negative. So here, my first term, when I plug in 0, it's positive. When I plug in 0 into this one, positive. When I plugged in 0 into this one, it's negative. So you're going to go with this -1 to the n instead of -1 to the n minus 1.
So we're thinking of the 1/1 factorial as our first term, and we're like not taking into account the other, like the zeros.
The zero, yes. The zeros, I mean, they could be there, but when you add 0 to something, it's really not changing anything, so you can just drop them off. Anything else? I kind of let the table dictate what's going on, okay? So maybe I'll go back up and we'll kind of recap from the table. When I was computing the table, I always start with 0 through 3. That's usually my default, but in this case I noticed I got a bunch of 0 terms which aren't going to be really included. They don't contribute anything. When I add 0, it's just not affecting anything. So that's why I increase the length of my table. It's because if I want to come up with a formula, I need enough terms to figure out a pattern. So I lengthened my table, and I write out my terms, and then you try to notice a pattern. So for me, when I noticed the pattern, I saw the signs changing, alternating series, and then I see only odd powers, which mean my exponents need to be 2n plus 1. This is a way of representing an odd number. It's an even number plus 1. All right. You ready to do this on your own? Okay. So I'll give you another function. So let's say, oh wait, I haven't done the radius of convergence yet for this one. So let's do that first before I give you that. So we need to find the radius of convergence, so I'm going to use the ratio test again. So we're going to plug in n plus 1 everywhere. And this is where you have to be careful with your parentheses. X to the 2n plus 1 plus 1. Oh, that's really small.
over 2, again put parentheses, n plus 1 factorial. And then I divide by that, so I flip it. Okay, that whole mess there. It's not very pretty. Again, you group up your like terms together. That's always what you do when you use the ratio test. -1 to the n plus 1, -1 to the n, x to the 2n plus 3, 2n plus 1 factorial over 2n plus 3 factorial. And then you simplify your grouped up terms together. So I'm getting -1, getting x squared. And then when I simplify these factorials, you should be getting 1 over 2n plus 3, 2n plus 2. Because then you'll get 2n plus 1 factorial and then they'll cancel. All right, so I'm getting 1. Normally, x has to stay inside of the absolute value, but this is x squared. X squared, can that be negative? No, it's a square. All square numbers are not negative. So I can actually drop the absolute value for that. This becomes x squared times 1 over 2n plus 3, 2n plus 2. So I can pull out the x squared, 1 over 2n plus 3, 2n plus 2, and what's that limit going to be? 1 over. The denominator is a really big number, right? It's 0. So I get the same thing I got in the last one. I get x squared times 0. I get 0 for this limit, which means no matter what, I'm always getting a number less than 1. So this thing always converges. So again, our radius of convergence is going to be infinity here. Mm-hmm. Yep. So when you write from here to here, right? When you write 2n plus 3 factorial, you're going to rewrite that as 2n plus 3 times 2n plus 2 factorial, but the factorials still don't match, so I have to repeat that process again. So I'm going to rewrite it as, cancel that out, 2n plus 3, 2n plus 2, and then 2n plus 1 factorial. And now the factorials match, so they cancel. Okay. Okay. So I don't think I'm going to do that because I don't have enough time. But what's really cool is if you graph sine of x and you write out some of the terms in these power series and do that graphing thing I was doing last time, you'll start to see more and more terms you take, the better and better approximate for sine you're getting, which seems kind of crazy because sine is this crazy up and down thing. In your power series, you only have polynomial terms. So somehow if you take more and more polynomial terms, you're getting this kind of up and down shape going on.